Welcome to the deep dive. We're here to unpack complex topics, really give you the real story.
That's the goal.
And today, we're diving into something truly essential, for modern life.
Yeah.
Batteries.
Couldn't live without them, pretty much.
Right. They power literally everything. Your phone, maybe your car, the grid itself.
Mm-hmm.
And the world of energy storage is changing so fast. So we're here to shine a light on that journey for you.
Absolutely.
Our mission today, it's a focused look at two key battery technologies. You've got the established lithium-ion.
The current king, you could say.
Exactly. And then the intriguing emerging sodium-ion.
Our challenger.
And yeah, we'll definitely sneak a quick peek into the future. Solid-state batteries, we have to mention those.
Can't ignore them.
So we've gathered a stack of industry analyses, technical comparisons, the works. Our goal, extract the most important nuggets of knowledge for you.
Cut through the noise.
Yeah. Okay, let's unpack this. We want to get you up to speed on the fundamental differences, the pros, the cons, and what's next for these technologies.
Sounds good.
Yeah.
So just to quickly set the stage, we're talking electrochemical energy storage.
Right.
Essentially, how these batteries cleverly store and release electricity using chemical reactions. And both Li-ion and Na-ion are, well, they're rechargeable, secondary batteries.
Okay.
What's really fascinating, I think, is their shared core principle.
How they actually work.
Exactly. Both battery types operate by moving ions, either lithium ions, Li plus on or sodium ions, Na plus, they migrate back and forth between the positive and negative electrodes.
Through the electrolyte.
Through the electrolyte, yeah. During charging and discharging, it's this elegant little chemical dance that lets them store and release energy.
Okay, let's start with lithium-ion then. That's the one we probably interact with every single day.
Most likely, yes.
It's really been revolutionary for energy storage, hasn't it? It dominates the market.
For very good reasons, absolutely.
Its biggest strength is energy density, right? It packs a serious punch.
It does. Typically delivering, somewhere between 140 and 220 watt hours per kilogram.
That's the range, yeah. And that's why it transformed, your smartphone battery life, gave EVs their range.
Huge impact.
But here's something crucial, longevity. Cycle life. How many times you can charge and discharge it.
Right.
And our sources show a massive range here. Sometimes it's 2,000 cycles, sometimes up to 10,000.
Yeah, and some sources even point to maybe 1,500, 2,000 for certain types.
So what does that tell us? Li-ion isn't just one thing.
Exactly. It's really a diverse family of chemistries. Each one is optimized for different things: power, cost, lifespan. It's a trade-off.
Gotcha. Plus, its efficiency is pretty high.
Very good. Energy conversion efficiency is usually around 85% to 90%.
Then it responds fast.
Lightning fast, yeah. Often at millisecond levels.
So that robust performance, that explains why it's everywhere.
It really does.
Yeah.
Beyond your phone, think about electric vehicles just cruising silently.
Yeah.
Industrial forklifts lifting heavy loads.
Okay.
Cordless drills.
Right, power tools.
It's their ability to deliver those intense high current bursts that makes them so useful for, everything from tiny electronics to heavy-duty gear.
And they're flexible with charging, too, right? You can just top them up.
That's a big practical benefit. Partial charging on the go doesn't really damage them, unlike some older battery types.
Mm-hmm.
And when we talk Li-ion, you often hear about different flavors like LFP, lithium iron phosphate.
Right, LFP. That's common now.
Often chosen for safety and cost.
Yeah.
And then there's ternary, like NCM, nickel, cobalt, manganese.
Known for higher energy density.
Exactly. More range, often, but different trade-offs again.
Okay, but even with all these advantages, lithium-ion, it has its drawbacks. It's important we talk about those, too.
Absolutely. It's not perfect. One of the biggest concerns is the fire hazard.
Right. We hear about that sometimes.
Lithium itself is just, it's highly reactive. So damaged batteries can overheat, potentially catch fire, especially if water gets in or even just high humidity.
Which is why they're classified as dangerous goods for shipping.
Precisely. And they're also quite sensitive to temperature. They don't love the cold. Below about +5 Celsius or the heat above maybe 35 Celsius, performance drops off.
Okay. And what about the resources? The mining?
That's another major point. Extracting raw materials like cobalt, lithium, it's environmentally impactful.
How so?
Well, it often involves high water consumption, potential pollution, landscape changes. And there are documented concerns about labor conditions in some mining regions too, as our sources highlight.
So environmental and social costs.
Yes. And finally, disposal and recycling. They're tricky. The reactive components make them hazardous waste.
Right.
And getting a unified, low-emission, high-quality recycling process that recovers all the valuable materials, that's not really widely available yet. It's a challenge we're still working on.
Hmm.
Now look, despite these challenges, the advantages of Lion still outweigh the disadvantages for many, many applications.
Sure, that's why it's dominant.
And manufacturers are constantly working on improvements, optimizations, and of course, proper storage, proper handling those are crucial to reduce the risks.
Okay. So, Lion, the workhorse. Powerful, but with real challenges around safety, environment, resources.
That's a fair summary.
And those challenges have really spurred the search for alternatives, which brings us neatly to sodium ion.
The emerging challenger, as you
Yeah.
said.
Yeah, it's generating a lot of excitement, often pitched as, more sustainable, maybe safer.
And as we mentioned, it works on a very similar principle, just using sodium ions, not plus ag instead of lithium.
Right. Now, the initial buzz around ion, a lot of it was about cost, wasn't it?
Absolutely.
The thinking was sodium is everywhere, it's abundant, way more than lithium, so it should be cheaper.
That was the logic, yes.
Yeah.
But the market, as you said, can be a tricky beast.
So what's the reality now?
Well, here's where it gets really interesting and a bit nuanced based on our sources. One source, HuntKey, points out that the recent drastic drop in lithium carbonate prices.
Oh yeah, lithium got much cheaper recently.
Exactly. And that has actually wiped out, or at least significantly reduced, Nizin's perceived cost advantage for now.
Really? So Lion is cheaper currently.
According to this analysis, yes. Current LFP lithium batteries are priced around, let's see, 0.47 yuan per watt hour, while Nion cells are more like 0.67 yuan per watt hour.
Wow, that's like 30% more expensive for sodium ion right now.
At the same performance level, based on that data, yes.
Yeah.
So Lion, specifically LFP, is actually more economical at this exact moment.
That is a fascinating twist. So the cheaper sodium narrative isn't quite holding up today. But wait, I see another source, source 3. It still describes NA as potentially lower cost.
Right.
So what does that mean? Is it just a matter of time or different assumptions?
It's likely a combination. It signals that the potential based on raw material abundance is still there. Sodium is fundamentally cheaper and more widespread than lithium. But current manufacturing scale, supply chains, optimization levels for neon haven't caught up perhaps. And as we saw, lithium market prices fluctuate wildly.
So it's definitely a moving target.
Absolutely. Material abundance doesn't instantly mean cheaper batteries on the shelf. There's a whole industrial process involved. So cost is one thing, but it's complex and shifting. What about the actual performance differences, the trade-offs?
Right, let's dig into those specs. Energy density first. How much energy can it actually store?
This is a key
But
difference.
Neon generally comes in lower here than Lion, right?
Typically, yes. Our sources suggest neon is usually in the 120 to maybe 175 Weishkg range.
Compared to Lion, which can hit, 250 Weishkg for those higher-end ternary types? And even LFP is often 150, 180 Weishkg.
Correct. And that density gap, well, it has real-world consequences.
Like for electric cars.
Exactly. In the automotive world, this currently limits neon mostly to things like low-speed vehicles, smaller city cars, 8-foul class cars, they call them, or maybe models with a range under about 400 kilometers.
So for bigger cars, longer range, Lion still has the edge.
For now, yes. The higher energy density is still needed for those applications. It really highlights matching the battery tech to the specific need.
Okay. Now, cycle life. This is where I got really interested because our sources seem to conflict quite a bit.
Yes, that's a fantastic point.
Yeah.
And it really shows how fast this field is moving.
So what's the discrepancy?
Well, one source, HuntKey again, suggests neon cycle times are generally around 2,000 to 3,000 times.
Okay, 2,000 to 3,000.
And they attribute this partly to the sodium ion itself. It's physically larger than a lithium ion.
Right.
So it's harder for it to kind of squeeze in and out of the electrode materials efficiently. That's called intercalation and deintercalation.
And that causes more wear and tear over time.
It can lead to irreversible structural changes, reducing the lifespan. And they compare that 2-3K cycles to LFP Lion, which they put at 3,000, 6,000 cycles.
Okay, so that source suggests Lion, LFP, less longer.
In terms of cycles, yes.
Right.
But then you look at source 3, and it claims neon batteries can achieve over 10,000 cycles.
10,000. That's way more than the 1,500, 2,000 cycles that same source mentioned for Lion in its comparison.
Exactly. A massive difference in the reported numbers.
So what's going on there? How can both be right?
That's the million-dollar question, isn't it? It could be reflecting different stages of development. Maybe source 3 is looking at newer, cutting-edge neon chemistries.
Or specific breakthroughs from certain companies.
Possibly. Or maybe it's lab conditions versus more realistic real-world use. or just different specific types of lithium and neon being compared.
So it really underscores how dynamic this all is. Research is ongoing.
Absolutely. It highlights that we shouldn't view nanon or lithium as monolithic blocks. There's huge variation within each category, and things are evolving rapidly.
Fascinating. Okay, so cycle life is, well, it's an area to watch closely with conflicting data points right now.
Definitely.
But beyond cycle life, there seems to be a clear win for Nanon in one area, cold weather.
Ah, yes, that's a significant advantage highlighted in Source 3.
It performs really well, even in extreme cold, down to like -30, -40 Celsius.
That's what the data suggests, yes.
Yeah.
Which is notably better than most standard lithium batteries, which can really struggle in the cold.
That's huge for places with harsh winters, Canada, Northern Europe, parts of the U.S.
Absolutely, the distinct edge for neon in those climates.
And what about safety? We talked about Lion's fire risk. Is Nion inherently safer?
Generally, it's considered to have high safety. Sodium is less reactive than lithium, and we are seeing certifications emerging, like the GB standard mentioned in Source 3.
So, potentially safer chemistry?
Potentially, yes. That inherent safety, combined with avoiding lithium, makes it appealing where fire risk is a top concern.
Okay, and one last point that seems really important on the practical side. Making them.
The production process compatibility. Yes, this is key.
So the sources say Nion production is very similar to Lion.
Remarkably similar. They can use much of the same equipment, the same production lines, with only minor tweaks.
So factories already making Lion could switch over or add Nion lines relatively easily.
Exactly. It means potentially very low replacement costs for existing manufacturers who want to diversify or adopt Nion.
That's a massive advantage for speeding up adoption, surely. Less investment needed.
It really is a huge industrial plus point.
Okay, so we have this complex picture. Different strengths, weaknesses, evolving data. Where do these technologies actually fit best? What are the ideal jobs for them? And yeah, what's next?
Good questions. For sodium ion, based on its current profile, decent density but not top tier, good safety, great cold performance, potentially lower cost eventually.
Right.
Its sweet spots right now seem to be things like two-wheelers, e-bikes, scooters,
Makes sense.
smaller city cars, those 80 or 80 class vehicles we mentioned, and certain energy storage applications.
Okay, energy storage, like for the grid or homes.
Potentially both, but there's a catch for grid-scale storage.
The cycle life again?
Bingo. Grid storage typically demands very long life,
Hmm.
often over 6,000 cycles, maybe even 10,000 more.
What?
So if Nayan's real-world cycle life is closer to that 2,000, 3,000 number from HuntKey, well, that's a hurdle.
But if the 10,000 plus cycle life from source 3 is achievable reliably and affordably,
Then it becomes a very strong contender for stationary storage, absolutely. It could be great for storing solar or wind power.
so the market is going to demand proof of that long cycle life and competitive pricing.
Exactly. Technological innovation needs to deliver on both fronts for Nayan to really capture a big share of that stationary storage market.
Okay. And looking further out, the next big thing everyone talks about, solid-state batteries.
Yes, the next frontier, as you called it. Often hyped as the future, especially for high-range, super-safe EVs.
What's the promise there? What makes them so special?
The potential is huge. We're talking estimated energy densities, maybe 300, 400 Havidam.
Wow, potentially double current Lion.
Possibly.
Yeah.
Very high safety because they replace the flammable liquid electrolyte with a solid one.
No liquid, no fire risk, essentially.
That's the idea. Plus, potentially good cold weather performance may be better than standard Lion, and faster charging maybe around 3C rate.
3C, meaning a full charge-in.
About 20 minutes. That's the target for some.
Okay, that sounds amazing. Higher density, safer, faster charging. Why don't we have them everywhere now?
Reality check time.
Uh-oh.
Solid-state technology is still very much in advanced research and development. It's incredibly complex to manufacture.
What's the main hurdle?
Making that solid electrolyte work perfectly. It needs to conduct ions well, but be stable, durable, and make perfect contact with the electrodes over thousands of cycles. That's a massive engineering challenge.
So production costs are high.
Very high right now. And scaling up production reliably, affordably, ensuring safety and longevity, that's going to take time.
How much time? Are we talking next year?
Definitely not next year for mass production.
Yeah.
Most realistic estimates put widespread commercialization years beyond 2025. It's a medium to long-term prospect.
Got it. So solid state is the future promise, but not the immediate solution.
Exactly. If we try to connect all these dots, pull back for the bigger picture,
Yeah.
it becomes really clear there isn't going to be one single best battery for everything.
Right. Different tools for different jobs.
Precisely. Neon looks like a concrete and imminent solution for specific niches.
Okay.
It offers a really good compromise on durability, safety, cold performance,
Mm-hmm.
especially in the short term.
Okay.
Lion, well, it's the incumbent. It's everywhere. It's constantly improving. Despite its limitations, it's not going away anytime soon.
Still the dominant force for now.
For now, yes.
Yeah.
And then solid state holds that breakthrough potential for the medium to long term if those industrial challenges can be cracked and costs come down.
So it's a really dynamic, evolving landscape, multiple technologies playing different roles.
That's exactly how it looks.
Okay, wow. We've covered a ton of ground today.
Right.
Let's try and recap the key takeaways.
Sounds good.
We started with lithium-ion, dominant, high energy density, but with those trade-offs. Safety concerns, resource extraction issues, recycling challenges.
Mm-hmm. The established standard with known issues.
Then we dug into sodium-ion. Really compelling advantages in specific areas like that great cold weather performance, the safety aspect, and the fact that it can use existing Li-ion production lines.
Big plus points.
But the current cost isn't necessarily lower than LFP Li-ion right now due to market shifts, and that huge question mark over its true cycle life, with sources giving really different numbers.
Yeah, the cost and cycle life are key areas where it still needs to prove itself at scale.
And finally, we glanced at solid state. The exciting future, potential high density, super safe, but still years away from being mainstream due to cost and manufacturing hurdles.
A long-term hope.
So for you listening, understanding these nuances, it's not just about batteries, is it? It's about seeing the real choices, the innovations, the trade-offs that are shaping our whole energy future.
Absolutely. These aren't just technical details. They affect everything from your gadgets to global energy policy.
So here's a final thought to leave you with. As our global hunger for energy storage just skyrockets, is the hunt for the perfect battery going to lead to one winner-takes-all technology?
Wow.
Or are we actually building towards a more diverse battery ecosystem? You know, where Li-ion, Neon, maybe solid state, maybe others we haven't even discussed, each find their perfect role, complementing each other to power our world.
A future with multiple solutions tailored to specific needs. It's an interesting possibility.
Something to think about. Keep exploring, keep questioning, and join us next time for another deep dive.